are. Let's look at table, oh, maybe not. There it is. Table 4.1 of your text. It shows the heat content. Another thing, and 102, you're probably well along with this, but learning how to read these tables and some of the graphs and whatnot in these texts takes some doing at times. It took me a long time, and get a lot of test questions directly from these tables. Plus, there's a lot of good information. This is showing the heat content, which is the net calorific value, and we'll go and talk about that a little bit, versus the CO2 emissions. The net calorific value takes into account the water vapor. All right, we'll go into that a little bit, but I don't want to get into that too much that I'd miss the major points of this table 4.1. Look at these fuels. Okay, we've got our four major fuels, our three fossil fuels, and we got old wood down here. The heat content as gigajoules per ton. Coal, now it ranges. You know, coal ranges from 20 up to 34 or so gigajoules per ton. Here they're calling this kind of coal, probably average 24 gigajoules per ton. Releasing 94 kilograms per gigajoule. Now you know how to read those headings? When I first got in this course and was looking at those headings, I got so confused. I thought they were talking CO2 released per kilogram something. No, that slash or that backslash just is a division, okay? The heading on that column is CO2 released. The unit is kilogram per gigajoule, all right? Fuel oil, which we don't burn much of, some. Back east, they burn more fuel oil in here. They don't have as much natural gas. 41 gigajoule per ton, releasing 79 CO2, 79 kilograms CO2 per gigajoule. I want to look at natural gas. Good heat content, double coal, and less CO2. And there's a reason for that. The main constituent of natural gas is methane, CH4. Coal is carbon, and the stoichiometric mix on coal, CO2 per coal is about 3.5, a little over 3.5 units of carbon dioxide per unit of carbon per unit of coal as carbon, whereas for natural gas it's more like 2.5, so it's less. The other thing about natural gas is, now it's a fossil fuel, you know, it's from the earth, same as coal, and there's trouble getting it, and there's a lot goes on to getting it with fracking and everything. But natural gas does not have sulfur in it to any degree. When you burn it, you don't have a particulate you have to take care of. So you don't have acid rain potential. And you put out less carbon. So it's a temporary good solution. Hopefully very temporary. Still a lot of CO2. Look at air-dried wood at 15 heat content, and this is air-dried wood at 80% moisture, which, yeah, if you maybe spread it out somewhere, it's going to get to there before you burn it. But you're going to have a big pile. It's going to be like 60% at best, maybe 50. So the heat contents could be down more like 6. But the CO2 released is pretty high, 80. But there's a caveat there. What is that caveat? Read that star. Yeah, Yeah, wood can be provided if, and a big, big fat if, the wood is harvested sustainably close to CO2 neutral. Of course, you got to transport the wood. You're going to burn some kind of fuel getting the wood to where you burn it in your boiler. So it's not going to be neutral totally, but it's a heck of a lot closer to being neutral than these other fuels. Way more close. And that was the idea behind the boiler at the U of M plant, to reduce the footprint from Missoula. And of course the neighborhood got involved, didn't like the idea of the trucks coming through and all that jazz and other things. And they had the bells and whistles on that boiler plant for control of pollutants from the wood, and we'll get into that in later parts of this biofuels, part of this bioenergy, about the pollutants from wood, particulate and the nitrous oxides. Anytime you burn anything, you got nitrogen in the air, and depending on how you burn it, you're going to end up with some kind of nitrous materials coming off. And they actually have a scrubber to take out the nitrous oxides. Okay? So, it's unfortunate we can't harvest more by wood for these purposes, rather than letting it burn up all summer. But table 4.2, I think, just goes into that and a little bit more, gives you more biofuels to look at, and you can see the listing there, and see the 60% moisture wood. So that's 40% dry, which is, we had 45, 50, down to 6 gigajoules per ton because of all the water in there. And this table is basically comparing the energy contents. Dried gum really has pretty decent energy content. Of course, charcoal's got quite good. You see, completely dried wood, no moisture in there, is up to 18 gigajoules per ton. And down to the very bottom again is coal, natural gas, and domestic oil. The other thing this table is doing is looking at the energy content as volume. That's the right-hand column. And again, the wood's down there pretty low as an energy content per volume. A reason bioenergy yet does not have as big a play in things. You got low volumetric energy content, you get in transportation, storage issues. Okay. Before I go to this, in case I run out of time, let's, I do want to get let's look at figure 4.4, and I'll call it up here before I go into this box on water. This is I remember when I first read this chapter, here I am, Mr. Bioenergy, I was getting confused. It kind of rolls right into a bunch of different things. Once I took the time to look at this figure and understand it a little bit, it kind of helped to categorize bioenergy in my mind, all right? And kind of helps lay out, I think, what this chapter is trying to tell us in about bioenergy. So, so it organizes, I guess, bioenergy by, whoops, by source, process, whether it be bio, chemical, physical, sizing, yeah, better, thermal. So let me quit doing this. Let's call it up if I can find it. There it is. Aha. Let's take a look at this thing. So look at the key down at the bottom. Color coded. Whoa. Physical processes, chemical thermal processes, and biochemical processes. The left hand black print listings are the sources. Okay, so you got woody plant material which can be processed via direct combustion. We all know that. We can burn it, make heat out of it. Of course, that heat could drive an engine. That heat could drive a turbine. It makes electricity. Heat our home. Of course, size reduction, possibly pelletizing. Great advantage off doing that. We absolutely did sizing at the mill. We sized the wood toward different kinds of digesters based on type of digesters. We sized our wood to a couple different kinds of boilers based on their capability of doing those sizes. And pelletizing, of course, you increase the volumetric density, reduce transportation costs. Maybe some of you have pellet stoves at home. Into solid fuels to make heat. Pyrolysis, liquefaction, is talked about in the book. Very, very high heat in the absence of oxygen to make solid or gaseous fuels, and straight gasification. And I hope you'll be able to see through this curricula the biogasifier out by the airport at the Montech facility. Ryan Kearns' deal. It's on a trailer, flatbed trailer, and it's a combustion unit taking screened wood, making gas like natural gas, like methane. That gas is burned in a engine, truck engine. Actually, it's converted to a natural gas engine, okay? And that engine drives a turbine, makes electricity that's supplied to the facility out there. I don't know if it's running yet. It takes a lot of attention. When you ran out of grant money to have someone take attention to it, it wasn't running anymore. But it's a neat process. And that brings me to his class on bioenergy as dynamite. This kind of delves into it. His gets into the details of bioenergies. And that's a neat facility out there. And it really shows what can be done with wood, okay, with bioenergy. Okay, he's also got cellulosic plant material. I always have a tough time saying that. Again, you can burn it. Now that material will anaerobically digest. You can go to a digester where the material biologically decays in the absence of air. That's anaerobic, making a gaseous fuel that can be made into heat, which is heat or can drive an engine. Then you get oily plant material, which can be extracted, okay, and converted to a liquid fuel. We all have seen articles on oily plant material. Microorganisms, algae, same kind of process. I missed to start sugary plant materials, fermentation, ethanol, liquid fuel. And of course there are the wastes, human wastes, livestock wastes, that can go through anaerobic digestion. And the residues from these oily plant extractions can also go through anaerobic digestion and go through these processes. But as you read this chapter, and you get maybe getting kind of, where are we at here, what's going on? You know, kind of was jumping from one to the other, and I was pretty attuned to the wood. You get to algae, and I'll go, well, what? Well, this kind of helped put it in its place. Yeah, kind of helped. A lot going on with algae. I'm not up to date, but that's a real possibility. You bet. A lot of advantages to algae as a bioenergy source. Okay. Let's go to table 4.3 just momentarily here. Another further breakdown. Yeah, better with it. I guess this table's not really too hard to understand, but again, and there's a good word, it helps categorize the different biomass energy sources. What components in those sources make it a good potential renewable energy source? Its resistance to natural decay. That's a big deal. That's huge. We had to have chips around for a long time. We couldn't chance running out of chips at the mill. It's a week to get that thing running. And about 4 days to shut it down if you could run out. So wood can decay. We had to be careful to be sure, and it took a lot of work for people, that first stuff in was first stuff out, and rotated our chip piles. Because the stuff on the bottom will decay. But its resistance to decay is higher, wood's higher than any of the other materials we're talking about here. So those are issues with those materials. Cellulose, or let's say oily crops, or even starch or sugar crops, you can't have that laying around a long time before you process it. So that might be an issue. You might have to have the plant pretty close to where those materials are. Okay, an example is trees for wood, grasses, and the text goes through that, but again, this table helps categorize cereals, oilseeds, microalgae, and typical yields. Look at the units. What are the units there in that last column? Anybody tell me? It reads funny. Tell me what that is.
Tons per, is that like a hectare per year?
Hectare, yeah. I always said hectare, and I would get thrown out of the room. But finally, after years of doing this, they corrected me. Yeah, hectare per year. How much is a hectare? How many?
I feel like there's 2.7.
Well, let's look at our appendix.
We were doing this on Tuesday, right?
Yeah.
Oh, you guys did look at this?
No, we just did another thing with hectares, so we had to convert them to acres.
Yeah, yeah. Yeah, yeah. So a hectare, it's in here somewhere, I thought. Mass, quantity, area, volume. There, table 8.3, got to be in the volume.
Area.
Next page, no?
It's in the area spot.
Area, yeah, it wouldn't be volume. Thank you. That's two. The areas, areas two cubes. So a hectare is approximately equal to 10,000 square meters. Well, what is that compared to what we do? How many, okay, let's do that. What we got here? Oh, that's perfect. Yeah, this is a good one. I did this last year, and it's actually in the notes still, last I looked. But let's look at this. So if there are let's go here. There. $10,000 square meters per hectare. How many football fields is that? We all know about what a football field, isn't it? Uh-oh, I don't have the top of my hand. How wide is one? 40 yards, maybe?
Is that right?
Yeah, so let's do this. So if a field is, how many yards per meter? Maybe this has got it in here. Yeah, 1 meter is 1.094 yards. Pretty close. 1.094 yards per meter. Okay. So 10,000 square meters, right? Divided by, it's almost the same, 1.094 squared, right? Yeah, per yard, okay. So it's roughly 10,000 divided by 1, right? That's kind of a senseless thing. So we got about 10,000 yards. That's all right. Square yards. But I can't do it that way, okay. Let's go the other way here, it's in the book. Let's do it a different way. Let's do feet. Let's do feet, I like feet better. So 10,000 square meters. This is one I can remember. There's 3.28, isn't it? Feet per meter. Yep. There we go. Now we got square feet, oops, per square meter. Right? So that's about 9, right? Or 10, right? It's about 10. So we got about 100,000 square feet. There we go. In a hectare. Right? We just said football field's 300 feet long by, what, 120 feet wide? I've got it right here.
Yards.
Yeah, 300, no, it's 100 yards long. Let me look at something here. Real quick. Yeah. Oh, that's approximated, I think. A football field's about 40 yards wide, isn't it?
Yeah.
Is that right? Yeah.
Yeah, it's like 100.
300 feet by, oh, I lost it. Oops. There we go. So by 40 yards, that would be 120 feet, right? So a football field is 300 by 120. What's that approximately? 3.6. How many zeros have we got? 2 times 2 is 4. 36,000 square feet, football field. Does that look right? Yeah. Yeah. So, 100,000 square foot per hectare, 36,000 square foot in a field, we got about 3 football fields, right? 2.5? So we're looking at this table. Yeah, okay, 2 3/4, thank you. It's a better number. Roughly, that's fine. Oh, I don't know, but look at this table. What's the number of that table again? 4 point? Did I lose it? Yep. What page is that table on? Is the next one? 4.5? 4 point?
129.
Page 129, thank you. Yeah, 4.3? Yeah. We're looking at woody biomass in temperate climates like ours as having a yield of 10 metric tons of wood per hectare per year. Okay, so it takes about 2 3/4 football fields of land to grow 10 tons of wood. Okay, how much wood was in that rail car? Do you remember? Yeah, how many metric tons did that? We didn't do it, did we? 80,000 pounds is about. Well, we can look it up in our index. Let's do that. This is how we get a visual of things. £80,000. How many tons per pound? Metric ton per pound. Is that back there, or have we got to calculate it out like we did? I know it's going to be about 0.54. We can do it this way. 80,000 pounds is right here. I know how to do it. Equals to. There you go. I'll just go in there. 2205 pounds per metric ton. There you go. What's that? 80,000 divided by 2205. Who's got that one? Yeah, that's what the number we get. So it's 36 tons in that car. Well, in 2.5 football fields, we're only growing about 1/3 of a car. Okay? So it takes some land. It takes some land. However, we've got a lot of land with trees on it we're not going to do anything with otherwise. You know? Except let it burn up. Pardon me?
Is that the, like, every tree on the acre, or is that just sustainably harvesting them so you take, like, the full-grown trees only? Or is it like every
No, I think that's the average.
Okay.
You know, in temperate climate, it might be, what, 30 years before you can harvest that tree?
Yeah, yeah.
And that's what it averages over that period of time?
Okay.
Yeah.
So they just
Maybe even longer. You know, it depends on what kind of trees. They talking deciduous here? They don't say. Oh, deciduous, yeah, they're talking hardwood, so it's less time than that. They grow faster than our pine trees, yeah. But again, it's a problem with temperate climates. If we're in the tropics or somewhere where the trees grow faster, the yields are higher, and that's what we see on this table. Yeah, good question, excellent. Yeah. And you're not going to grow. I think Tim got there. biomass where you can sustainably grow and economically produce food. We've got a world without food. We've got a world without enough food. I think those countries are going to want to go, grow some machanthus or whatever it is for burning in a boiler. Shoot, they need food before they need electricity. Some countries. Yeah. Okay, now I want to touch over my time. You got there's any questions? Thanks for your patience. I get into the numbers a bit much, but I think it's key to learning in this class. All right. You have a good night, you all. Thanks for coming. Oh yeah, Laura just made my day.
Guys gonna watch the football game?
Who's playing?
Ravens and Steelers?
Oh, are you a Steeler fan?
Ravens fan.
Oh, good. I was gonna go, oh my God, now I'm a Steeler fan.
I'm one of like 3 Ravens fans.